Gentlemen, we have come to the last paper of the seminar. I invite Mr. Vignesh Ramanan, immediate past chairman of the IAF Chennai chapter, to introduce our last speaker for the day, Mr. Venkatesh Selvaraj, Regional Manager Sales of South, Allied Refractory Products India Private Limited.
Foundrymen, it is my immense pleasure to introduce our next speaker, Mr. Venkatesh Selvaraj. Mr. Venkatesh is a seasoned mechanical engineer with over 15 years of diverse industry experience. He began his professional journey at Vedanta Aluminum Limited in Odisha, where he started as a graduate engineer trainee and rose to the role of assistant manager overseeing maintenance in the primary aluminum smelter. In 2014, he transitioned into the sales domain, joining Allied Refractory Products India Private Limited as a sales engineer. Over the last decade, he has steadily grown within the organization and now serves as the regional manager sales, leading sales and service operations across South India. His dedication and performance have not gone unnoticed. He has been recognized with a Sales Performance Award for excellence in the Foundry and heat treatment furnace segments by Allied Metal Products LLC, headquartered in Columbus, Ohio. Mr. Venkatesh is known for his customer-centric approach and frequently travels across the region to support clients with specialized refractory solutions. Outside of work, he is passionate about self-improvement. He enjoys reading self-help and management books and is very active at the gym. Please join me in welcoming Mr. Venkatesh Selvaraj.
So good afternoon to one and all present here. Thank you, Mr. Vicky, for the introduction. And thanks, IAF, for giving me an opportunity to deliver a speech in front of you. Before we directly jump into the presentation, I want all of you to imagine a scenario or situation. You are walking in a shop floor of your foundry and you are noticing a ladle is getting transferred, like let's say 5 ton of ladle, which is having steel at 16-20 degrees Celsius. It's traveling in front of you. And all of a sudden, you notice a red spot in the ladle. What will be your instant thought? So the situation is very scary, right? Yeah. So for some people, it is really a scary situation. So n number of thoughts comes into your mind. So how to safeguard your team, how to safeguard yourself, how to safeguard your equipment. So at moment you will be thinking like this situation or a problem could have been prevented. So it all starts with how we handle the first layer of protection, which is refractories. So the ladle refractories. So you will be going to listen about this particular ladle refractories for another 20-25 minutes. So that's the topic of the presentation. So advanced refractories for ladle and metal transfer, a guide to best practices. So myself, Venkatesh Selvaraj, handling sales South as a regional manager at Allied Refractory Products. So I made a presentation in few segments. Initially, we'll be giving like a quick introduction of who we are, and then what are the refractory requirements of a ladle, and what are the main properties we have to look into the ladle refractories, and then what are the classification of the castables, and then finally design changes, and at last we have some real life case studies at last. So to brief about Allied Refractory Products, Allied Refractory Products is a wholly owned subsidiary of Allied Mineral Products USA. It's founded in 1961. It's an ESOP company and financially solid. We have more than 1,000 plus employees globally, and we have 15 manufacturing locations and 8 manufacturing shape manufacturing facilities and 3 R&D facilities. We have sales activities over 130 plus countries, and we have like almost 160 plus trained sales and service professionals across the globe. And this is just a pictorial representation of our presence. These are all our manufacturing facilities spread across, and the color differentiation you can able to find our presence globally. In India, we are present in Gujarat, Sanand, behind the Tata Nano plant. So, what are ladles? Ladles is a piece of equipment which used to hold and transfer liquid metal. So traditionally, these ladles are not given much importance, which it has to be given. These ladles are always often lined with traditional practices like bricks and mortars, sand and sodium silicate, and then sand and CO2, sometimes fire clay. If you see, more refractory consumption takes place in the ladles compared to your induction furnaces. If we actually concentrate on these ladles, we can save a lot of overall cost, we can reduce a lot of manpower, and in fact, we can increase the quality of metal because ladle is the last point of contact of your metal before the molds. And each foundry is unique. So there is no one product suits for all. So let's say you have a different kind of metal. So you need to use different kind of refractories according to your metal chemistry, according to your slag chemistry, according to your operations. So there is no any one product fit for all the applications. These refractories has to be engineered properly to run longer, to run safer, and less cost per ton of liquid metal transferred. And further, it has to be having less reheat, which further lowers your fuel cost, lowering the surface defects, and lowering your inclusions defects in your castings. So in the next segment, we'll see what are the main important parameters or properties required for your ladle refractories. The first one is thermal shock resistance and mechanical strength, abrasion resistance, non-wetting properties, binders, erosion resistance, and insulation properties. So we'll see each properties in detailed manner. So thermal shock resistance is the first and foremost important property of your ladle refractory. When you consider the induction furnace, as soon as you tap out the metal, it is always in hot condition. Whereas in the ladle, you will be transferring the metal and the ladle will be idle, exposed to the atmosphere. And there is a huge, enormous amount of thermal shock involved compared to the induction furnace. So our refractory should have more thermal shock resistance. Thermal shock resistance is nothing but a property to withstand sudden and rapid temperature change without cracking or failing. So there are like two data points in the properties you can see to know whether this product is thermally stable or not. One main property is the thermal shock data. Some products will be given directly the thermal shock data, some may not be given. So we have to indirectly interpret whether this product is thermally stable or not. So one particular parameter is that this shock data. So this unshocked CMOR. This MOR means like modulus of rupture. Modulus of rupture is a property of a material, a maximum tensile strength a material can withstand upon loading, upon bending, sorry. So this test can be done either in cold condition or in hot condition. So this sample is been analyzed, unshocked, and it has a CMOR of 24.3 megapascal. And this particular specimen is been cycled for 5 times around 1200 degrees Celsius. And again, this test been conducted and seen the MOR. So the difference is not much. So it means that this product will withstand the thermal shock. So the strength retained is almost 100%. So this product is thermally stable. Likewise, if you don't have a data of thermal shock resistance, we can indirectly take it from the permanent linear change. So this is the data. If you see this particular product around 815 degrees Celsius and 1095, the permanent linear change is like negative 0.2 to negative 0.4. So generally, a product is stable if this difference in the permanent linear change should be less than 0.3. So it is just less than 0.2. So this product will perform better. So this is the indirect way of deriving the thermal shock resistance. And our traditional refractories like bricks and mortars, basically bricks have many joints, 6 joints. When you do the thermal shocking, these joints, there is a chance of getting opened up and metal can get penetrated through the joints. So we need to have a proper engineered refractory system in the ladles, which can sustain this thermal shock. And the mechanical strength. This can be calculated from cold crushing strength. CCS is known as compressive strength, its ability of material to withstand compressive force without fracturing. So if you see this particular product having highest cold crushing strength around 1095 degrees Celsius, around 135 megapascal. So likewise, we can analyze whether this product is mechanically strong, because ladles of bigger sizes like 5 ton, 10 ton, 20 ton and all have a huge metal in the ladle. It has to have a good mechanical strength to hold that particular amount of liquid metal. And third property is abrasion resistance. Material's ability to withstand wear and erosion from moving particles, especially at high temperature. These ladles, we generally give a lot of abrasions to remove the slag deposited in that, and sometimes if metal is getting solidified, you have to give a lot of abrasion force to remove the solidified metal. So this product has to have good abrasion resistance. In general terms, this abrasion loss will be given in the data sheets. If it is less than 6, it's considered a good abrasion resistant product. And sometimes all the data, important data parameters may not be given in the data sheet. We have to correlate with the other properties to have an idea. So you can correlate this particular abrasion resistance with the cold crushing strength. If this product is having higher cold crushing strength, it is directly proportionate so that it is having good abrasion resistance. So another major important properties is non-wetting agent. So apart from the aggregates, there are certain additives being added to the refractory system where it resists the liquid metal or the slag to adhere to the main working lining, so that you will be having the same volume of your ladle for a longer period of time. And another property is that binding agents. What kind of binding system we are using in your ladles? Either it's a calcium aluminate cement or fast bonded or like salt gel technology like colloidal silica, etc. These binders are important because when it depends upon the applications. For example, you're going to patch your ladle. It has been already lined with calcium aluminate system. You cannot have again the calcium aluminate system for patching purposes, because already fired dried refractory will not adhere with the new castable system. So in that particular case, you have to use phosphate bonded system, which will be adhere to the old dried refractory in much better way compared to the calcium aluminate cement system. And another property is that erosion resistance. So your refractory should not erode either in chemical way or mechanical way. So you are using like a bigger ladle like 5 or 10 ton capacity, and the liquid metal stream will be almost like it will be falling from like 3 or 4 meter height. So the bottom of your ladle get eroded faster. So your refractory should have better erosion resistance. So generally speaking, if you have a silicon carbide additive into your refractory, this will be having better abrasion resistance and mechanical resistance, erosion. And also you have to use the refractory which is compatible with your metal chemistry. You cannot use the chemistry which is not compatible for your metal and slag. Otherwise, you will be having a chemical erosion. And obviously, your refractory should have a very lesser K value so that your ladle can hold the temperature for a longer period of time. So as of now, we have seen what are the main important properties required for the ladle refractories. Now we'll see about the classification based on the cement content into it. So from long time, people are used to use high cement castables. It is called conventional cement castables, which is having like more than 2.5% of calcium oxide. So this is very easy to use. People are very fond of it. They can mix it with water at any amount of water, and they can easily travel it to any surface. So as I said earlier, there is no one product suit for all application. And the second comes as a low cement castable, which is having very less, like 1 to 2.5% of calcium oxide. It takes very minimum water. And there is another category called ultra low cement castable, which is like 0.2 to 1% calcium oxide. And the final category is like no cement castable, which is completely different binding system like phosphate bonded or colloidal silica. So when you see the high cement based castables, it requires very less mixing, less intensity mixing, and high level of cement. When the cement level is high, there obviously the water percentage will be more. So the density goes down, and a lot of water is in the system. It's always difficult to take all the water from the system, and it is having very less strength. On the other hand, this is the best suitable system for your ladle refractories, low cement based castables. Even though it requires like some specialized equipments like a pan mixer, needle vibrator, but the product has to be installed in a way it has been designed. certain product are designed only for a vibration cast. If that is designed only for a vibration cast, it has to be used with a pencil or needle vibrator. And the compared to the high cement refractories, low cement refractories need a shear force to mix properly. So that's the reason we always recommend to go with a pan mixer. It cannot be mixed in the hand. When you try to mix a low cement castable with the hand, you tend to add more water, which ultimately reduces the density of the product. Ultimately, it reduces the strength and lesser lining life. So this chart gives a general idea about the cement percentage and porosity percentage and the strength. So if you see high cement has very high porosity level and then very less strength. So 15 to 30 megapascal and 3 to 7 megapascal modulus of rupture at 1100 degrees Celsius. So low cement is having 70 megapascal and ultra low cement has more than up to 130 megapascal you can able to achieve the strength. So at the same time we cannot have ultra low cement for all the applications because it contains some special raw materials and special additives, so it may be expensive, but we have to think and decide the product according to the needs. When you see about the calcium aluminate cement based castable system, one main major part comes as a dry out. So whatever water we are going to add has to be removed without damaging the refractory system. So the physical water, whatever we are adding, 6 to 7% in low cement system, will come out around 100 degrees Celsius as a vapor, water vapor. But it is not the same. In traditionally, people used to put wood firing and they put some other system and all. But it is not sufficient to drive out all the moisture. When the water is added into the cement, it has some hydration phases. So complete chemical moisture will come out only after 550 degrees Celsius. So your ladle has to be heated minimum of 550 degrees Celsius, and according to your lining thickness, this ramp and hole system has to be designed. Let's say you're having like 4 inches of lining thickness. Your hole should be like 4 hours at individual levels like 120 degrees Celsius and 240, 360 and 550, etc. And we need to have a proper vent holes at your ladle shell. This allows the moisture to escape without damaging your refractory system. And this chart gives a fair idea about like what is the cycle generally being followed based on the different types of binding. So here you can see like the green shows low cement castable, which is having the highest number of hours dry out, compared to phosphate bonded or colloidal silica, which is having like half of the time of the dry out. And next comes the no cement based castable. It can be either phosphate bonded or colloidal silica technology. This technology employs colloidal suspension salt, which is like colloidal silica that transform into a gel network, which then solidifies into a ceramic material upon heating. So it is like having like suspended silica particles, which is a nanometer level, into some solution. So upon heating, it attains the strength. So this is having a drastic advantage compared to a traditional cement-based system. It is having very high hot strength and very high thermal shock resistance compared to the cement-based system. And only one thing we have to be very careful when we use this colloidal silica-based system is that it is having very less green strength. When you cast the ladle, you are not allowed to mechanically impact the castable because it is having very less strength. So once it is heated, it is having enormous strength. So that one particular point we have to remember when we are using colloidal silica-based system. And next comes a completely dry system. Depending upon the requirement, we can select the refractory accordingly. So this system contains special additives which can be self-firing. You have to line your ladle like same like your induction furnace. You have to fork, compact, and you have to bring up on the layers. And after you finish, you have to ignite the former either by torch or wood firing. So the self-firing additives will activate and it fires and hardens the material and it gets subsidized. So within like 3 to 4 hours, your ladle is ready to go. You can preheat the ladle and you can pour the metal in it. So we have covered so far basics, and we'll see what are the types of ladles and pouring system. So everyone is aware about different types of treatment ladles. So it can be either wire treatment or pocket type, segment type, auto pour or GF converter, etc. And pouring ladle, basically either lip pour or T-spot. Generally, this T-spot is further classified as 90-degree T or 45-degree T. Steel ladles generally have 90-degree T-spot, and iron foundries have pouring ladle of 45-degree T. And hand shank ladles, bottom pouring ladle, and tundish. So now we'll see like some design parameter, how we can improve the productivity. So in treatment ladle, generally the treatment ladle is designed in such a way that diameter is like 1:2 of the height. So if it is like 500 millimeter diameter, the 1 meter height will be there for the ladle. So it will always be difficult to maintain this particular pocket area or treatment area. So because the height is more, a person cannot go inside and do the repair work of the refractory. And moreover, the exothermic reaction happens in this treatment segment. So what we can do, we can segment the ladle into 2 pieces. And we can have a treatment pocket separately, and we can attach it to the upper shell. So in this way, we can have a proper approach to this treatment zone for a repair. And moreover, we can able to repair the upper case also as well easily. So even though the ladle is good, because we are not able to maintain the whole complete refractory has to be demolished and relined further. So in this way, we can avoid a lot of downtime. We can have a spare pocket area separately, get it ready. As soon as you can remove the old one and you can attach the new one, and your ladle is good to go. And the same system for your pouring ladle. A major bottleneck comes when you use the castable system in your pouring ladle, because your spout diameter will always be smaller to have a better heat loss. But this smaller diameter of spout always having a chance of getting clogged either by a slag or solidified metal. And you can have a spare spout whenever there is other issues happening. You can just remove and attach the new spout and go. And this is another design for steel ladles. Generally, steel ladles have a 90-degree spout. The same situation happens here also. Only for this particular area, people will be demolishing the complete ladle. So we can have like slight modification in the ladle. So we will have some slot like this. So this particular area can be casted separately, and this segment we can give you, try to give it as a precast or some dam design. You can place it on top of the existing ladle, and whenever there is a problem in the spout, you can just remove this particular dam and you can replace with the dam. So in that case, we can save a lot of castable. And this is like bottom pouring ladle design. This is our traditional way of designing the ladle. So we'll be having like ceramic fiber paper at the shell, and depending upon the need, we'll be either going with the insulation fabrics or super duty fabrics as a backup, and then 80% alumina castables like LCF 384 for the steel ladles. So this is the way of lining. So now we'll have a look about tundish design. The same way, tundish is also like used to transfer the metal. Continuously metal will be holded in the tundish, and there is always abrasion will be happening in the tundish. So this tundish also has to be designed according to the need of the properties. So we can either go with ultra low cement castables like VCAS 426, which is having like silicon carbide, which will help in abrasion loss, and it gives a non-wetting property so that buildup will not be happening in the tundish system. So these are like certain pictures of how we do the tundish. So now we'll look into the real life case studies. So this case study 1 consists of the same tundish. Objective is to run the tundish for 6 days stretch instead of stopping for a change of tundish every 3rd day. So this particular customer was pouring SG, and there used to be a build-up in the nozzle area. So every 3 days once they used to bring the tundish out, and they'll give the new tundish back in the line. So every time they do this process, they lose around 1.5 hours of time changing the tundish, which is around like 50 ton of production loss. So earlier material, what they were using, conventional castables, and what we changed is to ultra low cement castable, which was having like 12% of silicon carbide. By just changing this, we could able to achieve complete 6 day stretch without stopping for 3 days. Productivity was increased. Not only the productivity is increased, we have been cost effective as well. We generally say like price versus cost. when we are buying certain items, we don't need to look about the initial cost of a product. We need to see what is the overall ownership of a product. Let's say we buy a shirt of 1,000 rupees, but you will keep on spending money and repairing those items. You have to consider the overall cost of ownership instead of just looking at the initial cost. So the same way, if you see their initial cost was around 1 lakh rupee in their method, and our cost was around 3.6 lakhs. So they used to patch around 150 kgs of their regular patching material, which is coming around 9,000 rupees. And their total cost of patching for 6 months is like around 5,40,000 rupees. So their total cost of a tundish for 6 months is around 6,45,000. Whereas in our patching is almost half of the patching, so it is around 6,14,000 rupees. So not only increase the productivity, we were able to be cost effective as well in the long run. And this case study is for pouring ladle to reduce the erosion in a 110 pouring ladle, which in turn reduce the buildup in the pressure pour. The processing temperature is 1450 to 1500 degrees Celsius. The life of their existing ladle is only 2 days, which is like 25 metric ton. So earlier they used to use sand and fire clay, and we changed it to low cement castable with ceramic paper. Obviously, when the refractory system is getting eroded, it obviously goes into your holding furnace or pressure pour system, which you may not be able to remove it completely. So it acts as a build-up to your receiving spout or throat. So here in their existing system, they used to use 300 kg of sand and fire clay. So their total throughput is only 25 metric ton. So the erosion after 25 metric ton is like 15%, which is like 45 kg of sand. So erosion per metric ton of throughput is like 1.8 kgs. After converting into low cement system, their lining life is like 1500 metric ton. Compared to 25 metric ton, the life was improved to 1500 metric ton. So the erosion per ton is like only 0.034 kg. And this is just a simple modification which can help you in heat loss. This is lining thickness of around 75 mm directly onto your shell. So if your hot phase temperature is 1450, if you don't use any insulation as a backup, you will be having like cold phase as 420 degrees Celsius, and heat loss through the refractory system is 16,210 watt per meter square. If you just incorporate 6 millimeter ceramic fiber paper, your cold phase temperature can be reduced to 356 and heat loss can be reduced up to 40%. Just by changing a paper, you can save enormous amount of heat which is transferring through your shell. So with the same line, I wanted to highlight one particular thing which all the foundry has to see. This is one steady state heat analysis for a 15 metric ton ladle, which for a metal of inconel. If you see the lining thickness and configuration, everything is same in both the side. Only change is that we are incorporated a cover of 50 mm blanket. So if you see the heat loss, temperature drop rate is like 5.79 Celsius per minute. For 10 minutes, the loss is like 57.9. By just introducing a ceramic blanket, we can reduce the temperature loss more than 80%. So generally we say the loss is through the radiation heat is more compared to the conduction through the shells. More than 80% losses through the top. So this has to be addressed in order to have like a better heat efficient refractory system. So with this I conclude my presentation. If there is any question, I'll be happy to answer.
No more.
Sir? Abrasion loss. Yes, sir. Sir, actually, we add additives like silicon carbide, which will improve your abrasion resistance. There is a test called, we'll take a specimen and sample according to the ASTM standards. So it will be injected with some abrasive particles for some particular time. And what is the loss in the specimen? Let's say like how much centimeter cube is been lost. It is calculated as an abrasion loss. So if the product is containing more silicon carbide, it will the loss will be very less. If your product is not having any silicon carbide, it will be losing more. So the abrasion loss will be more. Yeah, for rule of thumb, it should be less than 6, considered as a better abrasion resistance product. Yes, sir, as low as possible is good. Below 3.5 also some products are there, in which complete silicon carbide content will be more. Yeah.
Percentage of water addition, no?
Sir, generally high cement, it will be more than 10%. Low cement is like 6 to 7. Ultra low is further less than that. So this is 4 to 7, low cement. High cement is more than 10%.
Okay, thank you.
Yes, sir.
What would be the phosphorus pickup approximately?
So generally, phosphorus is not in the metal form, sir. It is in the oxide form. It is like P2O5, some pentaoxide. So generally, it doesn't come and contaminate your liquid metal. So it's just a binder. Once it binds and evaporates, it doesn't come into contact in your liquid metal, if I'm not wrong. Okay, but there may be a chances of initial dry out is not proper, but later it will be keep on diluted. If we didn't heat it properly, there may be a chance. Yeah. Any more questions, sir? If any more questions, I've given my contact details. You can reach me at my mobile and email address, and I'm open till the end of the session. I'll be available. You can contact me anytime.
Thank you, Venkatesh.
Thank you so much.
That brings us to the end of the last paper. Now I call upon Mr. R. Palani Murugan, Chairman of the IIF Southern Region, who has just returned from Belgaum's National Foundry celebrations, to be with us. Thank you, gentlemen. Gentlemen, this brings us to the conclusion of the 76th NFD seminar. We hope you found the 9 sessions insightful and rewarding.